Welcome to ATMOS 5000 Day 25. We're focusing in on sections 15.1 and 15.2 from Chapter 15 in the Stull textbook. We'll be talking about the different types of precipitation. We'll go into great detail about hail formation, damage, and mitigation strategies. And then we'll also talk about the formation of downbursts and gust fronts and the weather that's associated with those. Precipitation has lots of different categorizations. If we just talk about rainfall, we usually divide it into kind of drizzle, light rain or small rain droplets, and heavy rain, which is large rain droplets. Drizzle has droplet diameters between 0.2 and 0.5 millimeter. Small rain droplets have diameters between 0.5 millimeters and 2 millimeters. And large rain droplets are those with diameters essentially greater than 2 millimeters. And remember that there is an upper size limit for the large rain droplets because aerodynamic forces will break them apart if they get much larger than about 6 millimeters. In terms of frozen precipitation, the most common is what we refer to as graupel, and that is rimed ice crystals. Recall that riming is when supercooled cloud droplets freeze on contact with an ice crystal. And the graupel will be a white spongy type of fluff ball with a diameter less than 5 millimeters. And that graupel serves as an embryo for hail. And small hail, which is irregularly shaped ice, has a diameter greater than about 0.5 centimeters up to about 1.5 centimeters. And large hail is between 1.5 centimeters and 5 centimeter diameter. And then we have enormous hail, which is very rare but extremely dangerous. It has diameters greater than 5 centimeters. So those are essentially solid ice, as opposed to snow, which is just an agglomeration of ice crystals. It has a lot of empty space inside the snowflake, making its density very low compared to the other types of ice that we've talked about. And then there's sleet. Sleet are really pellets of ice. And they're typically frozen rain droplets or refrozen melted snowflakes. So they're different from graupel, but a lot of people kind of think that graupel and sleet are essentially kind of the same thing because they present themselves as smaller than small hail ice that falls out of the sky. One of the differences is that graupel is typically white and sleet is typically clear. And then we have freezing rain, which are essentially supercooled rain droplets which freeze on contact with the surface, whatever surface that might be, whether it be a car, a road, a house, leaves on a tree. They do a lot of damage to trees because of the weight that the trees pick up when the freezing rain coats them. And we have the latent energy release as a function of rainfall rate. So if we have this 1 meter by 1 meter square column of atmosphere, and we have a cloud in that column, and there will be latent heat energy release associated with the condensation. And we've done this calculation before, but now what we're doing is we're relating the latent heat release in this column, instead of being due strictly to the condensation, we're doing it strictly with the rainfall rate. Because as that rain falls out, there's no way for that liquid water to evaporate, which means that you won't have the exchange of energy back into the latent heat energy. And so the HRR is essentially your heating rate due to the rainfall rate is equal to a constant A, which is 694 joules per second per meter squared per millimeter per hour. And that RR is your rainfall rate in millimeters per hour. And the units of this heating rate due to the rainfall are going to be joules per second per meter squared. So it's kind of an integrated amount of energy in this entire column of atmosphere. And this column, of course, is the unit area of 1 meter squared. So focusing in on hail, hail comes in many sizes. Here we have some extremely large hail. I've personally never seen anything quite that big. The largest I've seen is about the size of a golf ball. So why are these hailstones white? Well, they're white because they have air bubbles that are trapped in the ice during the freezing process. So imagine that you have an ice crystal that's falling through supercooled clouds. Every time it touches a supercooled water droplet, that water droplet instantly freezes. And as these water droplets freeze, they don't have time to spread out evenly across the surface. So they trap air bubbles essentially inside the ice. And there are air pockets in there, and that air pockets will scatter the light differently, and that will basically appear white. The hail is extremely destructive, especially the large hail and the enormous hail. It does significant structural damage to roofs, windows, and siding. That's about $500 million annually. It does a lot of damage to vehicles. It dents them. It makes them look like a golf ball with all these dents all over them. It can break the windows. That's generally up to about $100 million annually, but by far the largest destructive impact of hail is crop damage. If a farmer happens to get a hailstorm over his farm, prior to harvest, it can completely decimate the field. It not only can destroy the leaves, it can break the stems, and the cost to society in the United States are about $1 billion annually. And the extremely large hail can even cause death of animals such as birds, cattle, and even people have been killed by hail. So why is hail so destructive? Well, it's because its terminal velocity is quite large. So as the hailstone diameter increases, up to around 5 centimeters, which would be, the extremely large hail, it's falling at 40 meters per second. And by the time you get to 10 centimeters, it's falling at about 55 meters per second. That's really fast, has a lot of momentum, and can do a lot of damage when it hits. So here's an example of asphalt shingles that have undergone hail damage. You can see the pocking where the material on top of the asphalt shingles has been bladed away by the hitting of the hailstones. Here we have hailstones that were coming down at an angle, and they were able to punch through the siding of this house and actually break the window. So here's a close-up of the vinyl siding that has had holes punched in it by hail coming down at an angle. Here we have a Volkswagen car that's had significant hail damage. If you look at the hood, you can see dents in the hood, and then you've got the broken windshield associated with it. I don't know why the car looks like it's smiling, but it definitely is in need of some attention. So here we have some large hailstones that broke the windshield on this car. Here we have an example of hail that destroyed the back window in this car. And if you look in the background, you'll see a lot of leaves on the ground. It's really common for hailstones to take the leaves off the trees as they're falling. And of course, you'll get these big dents in the hood of the car. You can get lots of little dents or a few big ones like this one. And of course, aircraft are not immune to hail damage as well. Can you imagine being the pilot flying through a cloud and encountering hail and having the windshield of the airplane crack? Now, luckily, these airplanes are designed to have two panes, an inner pane and an outer pane. This one destroyed the outer pane, but it would definitely get your attention. Of course, this aircraft had a little more damage than just the windscreen. Here you can see that the front of the airplane was completely destroyed by its encounter with hail. That's essentially the radar assembly inside the nose cone up there, which was exposed during this event. The leading edge of the wing was pelted and dented, essentially doing millions of dollars of damage to this aircraft. This is the cowling of the engine. So you had a lot of damage to the cowling, but they also have to inspect the fan blades inside the engine itself to see what kind of damage was done by the ingestion of these hydrometeors, these hailstones. Here we have an example of crop damage. This corn is not looking very good after its encounter with hail. Here we have corn that was significantly damaged by hail. It does not look very healthy. The leaves have been stripped off. Tassels are in bad shape. And here's an example of a stem that was completely knocked over. And if you look closely, you'll see these kind of white dead spots on the stem. And that's essentially where the hail was hitting it on the side as it was falling. The hail was falling at an angle. So how do these hail embryos form? So here we have this hypothetical cloud. We've got the freezing level at the bottom of the cloud, where the temperature transitions from 0 degrees C to colder than 0 degrees C. We have the supercooled zone of the cloud, where the temperatures are between about 0 and minus 15 degrees C. And then we have the region of the cloud that's most likely to glaciate, which are the places where the temperature is less than minus 15 degrees C. So we have liquid droplets in the bottom, supercooled droplets in the middle, and ice crystals are more likely in the top of this particular cloud. So these ice crystals essentially are falling. They have a fall speed as they fall through the supercooled droplets. The supercooled droplets are nucleated by contact. So as the ice crystal comes in contact with the supercooled cloud droplet, the supercooled cloud droplet will basically instantly freeze on the ice crystal. And then as it comes on down, it'll remain frozen until it melts on the way down. And because the fall speed of these hailstones is quite large, they tend to make it down to the surface before they melt. And of course, our grapple grows by the riming of supercooled droplets on an ice crystal seed. So here we have a image that shows the trajectories of air as it's drawn into a supercell thunderstorm. So we have the rain-free region, which is the bounded weak echo region, where the updrafts are so strong that they are pushing the rain droplets out of the way. The hail will typically form right on the periphery of the bounded weak echo region. So here's an example where we have no hail. We have an air parcel. In this case, this green droplet is going to follow a trajectory. It is going to take a ride right up through the middle of the core of the updraft of the supercell. And because it's right in the core, it's going to experience the fastest wind speeds, which means that it's going to move from the lower portion of the cloud to the higher portions of the cloud very rapidly. So let's watch what happens here. So this particular air parcel, this particular cloud droplet, if you will, made it all the way up to the top of the cloud because it was in the core of the updraft, and it probably turned to ice up near the top where it got really cold. And in this case, it's being detrained from the cloud at the upper levels and contributing to the fuzzy appearance in the anvil of the cloud. We'll contrast that with the path taken by a droplet / ice crystal that turns into hail. So in this case, it's actually going to start off and not be right in the center of the updraft, but let's follow the trajectory of this hydrometeor that turns into small hail. So what did it do? It was rising. It actually turned to ice up and kind of at the end of the initial trajectories labeled as 1. It got up high enough to nucleate, and then it fell back down. And as it was falling back down, where we have these numbers 2, it eventually fell back down into the supercooled zone where the temperature was essentially between about 0 and minus 15 degrees C. So at that point, what we have is we have a grapple particle. So it's an ice crystal that has been rimed, but then it gets brought back into the updraft on the periphery of the updraft, and it goes on a second journey through the supercooled droplets, but this time it's on the way up because it got back into the edge of the updraft. And that's labeled here as position 3. It's moving upward, and then eventually the hailstone becomes large enough that its terminal fall speed exceeds that of the updraft velocity, and after that point it will start to fall, and that is labeled as number 4 in this particular trajectory. So initially it rose, it turned to ice, it started to fall, it rimed, it turned into a grapple particle. That grapple particle was entrained back into the updraft on the edge of the updraft, and it went through the supercooled zone again and became larger and fell out as small hail, just on the edge of the kind of the bounded weak echo region. We'll contrast that with large hail. It's going to start off on the same trajectory. It's going to rise, it's going to turn to ice, it's going to then fall through the supercooled droplets and become a rimed grapple particle, and then it's going to get entrained back into the updraft, but this time it's going to kind of be on the periphery of the updraft initially, and it's basically going to grow larger because it spends more time in the rotating updraft than that for small hail. And so let's watch an animation of that. So you saw how this particular hailstone, while it was growing, spent more time in the bounded weak echo region, which is in this case the supercooled droplet collection zone, and it stayed in that zone longer because of the stronger updraft velocity in the core. And eventually, the hailstone became large enough that it overcame the updraft velocity and started to fall out. And what you'll find is that the large hail tends to fall closer to the updraft core. So it falls closer to the bounded weak echo region than the small hail did. So if we look at a supercell thunderstorm from above, we have the hook echo, which is your bounded weak echo region, which is denoted with the letter T here. That's if a tornado is going to form, that's where the tornado is most likely to form, because that's right underneath the wall cloud and the rotating mesocyclone. But what I'm trying to focus in on this one is where we have the anvil clouds, which are not really precipitating and not really reaching the ground. But then you have the light rain, the moderate rain, the heavy rain, the hail, which would be light hail followed by heavy hail, and then followed by a tornado. So if you happen to be trying to drive through this storm, that is the progression of the weather that you would see, and you certainly wouldn't want to try and punch through one of these supercell thunderstorms. Here we have the side view of the same sort of thing. So here we have the bounded weak echo region, which is the largest updrafts, the highest updrafts, and that's where the rotating mesocyclone is. And if you were driving from the northwest to the southeast through this supercell thunderstorm, you would once again have that progression of light rain, moderate rain, heavy rain and grapple, small hail, large hail, and then if you happen to punch through and there happen to be a tornado there, then you're in bad shape. So definitely don't recommend driving through a supercell thunderstorm. If you're doing storm chasing, it's best to approach from the backside of the storm and not be in the precipitation section of the storm where you can't see a tornado if it is going to occur anyway. So these hail stones falling out of a cumulonimbus cloud can accumulate several inches on the ground, and we refer to these swaths of hailstones that have covered the ground as hail streaks. They're actually very dangerous to drive on. They're unlike snow, they're like little tiny ball bearings. It's very difficult to keep your traction on these, but because these are ice that falls during the summer months, they typically melt within a short time period, depending upon how deep that layer actually is. But they're quite impressive when you see them. So there are two ways that these hailstones grow. One of these we refer to as wet hail growth. And this is, of course, the freezing of supercooled droplets or releasing latent heat. And if the ice crystal happens to be close to 0 degrees C, then the latent heat release can raise the temperature on the surface of the hail just a little bit above 0 degrees Celsius. And what that does is it allows the water to spread out before it freezes. And in this situation, you'll get a very smooth, round hailstone. Well, contrast that with dry hail growth, where the temperature of the hail surface remains below 0 degrees C, and now you have the the supercooled water droplets that are freezing immediately on contact. And because of the aerodynamics of these stones, or these hailstones, you can sometimes get spiky hailstones that are definitely not symmetrical. And if you take a hailstone, a large hailstone, and you slice it open, you can actually see whether or not and under what conditions this hailstone formed. So here we have this idealized slice through a hailstone showing the graupel embryo in the middle, and then we have clear ice and white ice that are alternating. So the clear ice would be the wet hail growth time periods, and the white ice would be the dry hail growth period. And all of these hailstones typically undergo a combination of both wet growth and dry growth. So if we look at where hail is most common in the United States, it is basically in Texas, Oklahoma, and Kansas. This coincides with the location of the supercell thunderstorm maximums. We often refer to this area as Tornado Alley because this is where these supercell thunderstorms are most common. If we look at the total hail reports that are greater than 2 inches, it also coincides with the Tornado Alley. And extends a little bit further south into Texas and a little bit further north into Nebraska. But you can see that this entire Midwestern region all the way up to North Dakota is an area where they do have common hail reports of hail greater than 2 inches in diameter. So let's look at how the progression of these hail events changes with the month of the year. So if we look at the January hail reports in the upper left, panel A, you'll see that the hail reports are primarily limited to the Gulf Coast states, Texas, Louisiana, Arkansas, Mississippi, Alabama, down that region. And if you think about that, in January, how many thunderstorms do you have in the upper Midwest in January? Not very many. And that just happens to be, that's where the thunderstorms are happening because that's where you have the proper conditions, the lift instability and the moisture. As you move into April, now you are definitely in the supercell thunderstorm month. April, May, and June are the months when these supercell thunderstorms are most common. And that's when you get that peak in the hail reports in the Texas, Oklahoma, Kansas corridor. As you move into late summer, the frequency of the supercell thunderstorms is down, but you still have these multi-cell thunderstorms that can generate hail, and they've actually moved much further north. And now the peak in the hail, the late summer hail, is actually kind of in Kansas, Nebraska, South Dakota, North Dakota. And of course, it's these late season hailstorms which are really damaging to crops. And so it's really this upper Midwest area where you have the most damage and the most economic loss associated with the hail damage to crops. And then by the time you move back to October, the storm activity is moving further south once again. If you look at the reports of the really large hailstones greater than 2 inches, they're very rare in January and October, but that April to July time period is when these super large hailstones are most likely to occur. And once again in April, it's coinciding with the location of those supercells down in Texas, Oklahoma, and southern Kansas. And by the time you get to July, that maximum has moved northward into South Dakota, Nebraska, and North Dakota. So let's just take a look at the world record hailstones. So no single hailstone holds all the records. We do have record hailstones for diameter, for circumference, and for weight. So let's take a look at these hailstones. The world record diameter for hailstones is 8 inches. The circumference is almost 19 inches, and the weight is almost 2 pounds. So here's Coffeyville, Kansas's claim to fame. There's not much to do in Coffeyville, Kansas. I grew up in Kansas. And back in 1970, they had this really enormous hailstone that had a diameter of 5.67 inches, a circumference of 17.5 inches, and it weighed 1.67 pounds. This hailstone was saved, collected, and was actually sliced open at the National Center for Atmospheric Research in Boulder, Colorado, so that they could look at the growth pattern. But clearly, it's undergone a lot of dry growth there at the end with all the spikes on it. So that was the world record hailstone for basically about 33 years. And then this hailstone fell in Aurora, Nebraska in 2003. And it had a diameter of 7 inches, a circumference of 18.75 inches, and the weight was not available because it wasn't stored properly, so they don't know what the maximum weight of this stone actually was. And then we had this monster, which fell in Vivian, South Dakota in 2010. It had an 8-inch diameter, 18.625-inch circumference, and it weighed just under 2 pounds. When it fell, it left a crater in the front yard of this house. You can see that it left quite an impression in the ground there. And this is the storm that produced the Vivian extremely large hailstone. It was quite impressive visually, and what we're looking at here is we're looking at a rear flank inflow into the supercell thunderstorm. The supercell thunderstorm is obviously too large to be seen in one picture, but here we have the rear flank inflow into the storm. On radar, we have the NEXRAD radar, and on radar, we look at the precipitation associated with this and the radar return signal. Of course, the green and the blue are the light precipitation, the yellow is the moderate precipitation, the red is the heavy precipitation, and light purple is often associated with extremely heavy precipitation, and the darker purple is typically indicative of hail. And so in this particular storm, we have a significant amount of purple inside the radar, indicating the presence of very large hailstones associated with this storm. And then we have the Doppler radar, and the Doppler radar is actually showing a vortex, a rotating vortex. So we have red touching green in the middle of this storm, and that can only occur if you have rotation in the storm. This storm actually did produce a tornado, but it also shows you where that mesoscale mesocyclone is actually located, and that's kind of the base of the bounded weak echo region. And one other way that you can use radar to determine whether or not there's hail in storms, other than just looking at the radar return signal, is you can actually use polarized radar. Uh, and this polarized radar basically puts out a beam in the vertical and then a beam in the horizontal axis. And if you have round hydrometeors, then you'll get the same return signal regardless of whether or not the beam is polarized in the vertical or the horizontal direction. But if you have really large rain droplets, of course the rain droplets are going to be flattened at the bottom, and so they're going to have a larger cross-sectional area for a larger radar return in the horizontal than they do in the vertical. And the hailstones tend to have pretty similar vertical and horizontal return signals. So what might you do to mitigate hail? Well, all hail mitigation techniques basically rely on seeding supercooled clouds with ice nuclei. And the reason they try and do that is because the way that we get the growth of the hail on the graupel embryos is that graupel moves through the area of supercooled droplets. If you don't have supercooled droplets, then you're not going to have hail growth. So by injecting ice nuclei into the supercooled region of the cloud, it will reduce the amount of supercooled water that's available and should theoretically reduce the amount of hail that forms. If you increase the number of ice crystals, you also promote competition for the available supercooled water. And instead of having all of that supercooled water end up on a few really large ice crystals that turn into hailstones, it'll be distributed on a whole bunch of ice crystals, and you'll get light rain out of the cloud as opposed to hail. Unfortunately, although in theory this sounds like a great idea, there's really no proof that hail suppression efforts are effective, just like there's no real proof that cloud seeding can actually statistically enhance the amount of precipitation that comes out of clouds. The big problem is that these are completely uncontrolled experiments, and it's not like you can have one cloud next to another. You seed one, you don't seed the other, and then you see what the results are, because every cloud is different, the environmental conditions are different, and it's just a really difficult thing to prove. So what is a downburst? Well, a downburst is a strong downdraft that originates in the lower part of a cumulus cloud and descends all the way down to the ground. These downbursts, surprisingly, actually don't require a strong thunderstorm. And when that wind hits the ground, it can generate strong straight line winds of up to 100 miles an hour and can do a lot of damage. So here we have a shallow, high-based cumulus cloud. So there's a long distance between where this cloud base is at and the ground. And we have a high liquid water or ice concentration core that is falling near the base of the cloud. And it's going to fall out towards the ground. And this precipitation, the ice in the water, falls, and it's falling into a subsaturated environment, which is going to cause some evaporation or sublimation or melting, which the hydrometeors need energy in order to evaporate or melt or sublimate. And they get that energy from the surrounding air, which cools the surrounding air and causes this air parcel to cool and to become negatively buoyant. And so it'll continue to accelerate downward because of this negative buoyancy, and air is drawn into the side of the clouds, which is entraining, which will actually dry out the lower part of the cloud even further. And then once this downdraft hits the ground, you have divergence at the ground. And you've got convergence inside the cloud, and that's feeding this downburst, and then you've got the divergence at the surface. And then that surface divergence peaks, the cloud precipitation is depleted, the cloud convergence weakens, and now you have these strong straight line winds that are moving out from the center of the downburst at speeds of up to 100 miles an hour. And then friction with the surface will eventually slow it down, and that downdraft is going to weaken rapidly because it's been cut off from the cloud and the precipitation, and you'll be left with this cold pool of air down on the ground, and the winds will quickly subside. So here we kind of have my idealized version of a downdraft. This is not a tornado, but this is a rain shaft that is coming down from the cloud. And when that air hits the ground, it spreads out, but it's spreading out in kind of 3 dimensions. And you'll get this rolls on the leading edge of the downdraft as well. And you can often see this when these downbursts hit a agricultural area. You'll see this donut-shaped dust moving out away from the center of the updraft with significant rotation on the leading edge of the downburst. So how do we differentiate that with a microburst? Well, a microburst is a downburst, but it's a small, intense one. And it has a diameter less than 4 kilometers, and it can be a wet microburst where you have visible precipitation, or it can be a dry microburst where you don't have any precipitation that's hitting the ground, but you might be able to see some virga, which is precipitation falling out of the cloud but evaporating on the way down. So here we happen to have a wet microburst. So we have this large cloud, we have a downdraft which is on the right of the image. It has come down, it has hit the ground, it's spreading out, and then you can see the leading edge of that rotating vortex, which is on the leading edge of the downburst, or in this case, the microburst. Here we have a wet microburst. So we have this cloud that has a precipitation shaft, and you can see that the wind is moving out away from this precipitation shaft, and it's picking up dust. And that's just showing visually where the edges of that microburst are actually at. And here we have an example of a dry microburst. So we have a cloud which is starting to precipitate, but it evaporates, but the air is still moving down. It's still negatively buoyant. When it hits the ground, it's then spreading out. And in this case, we have a fairly strong wind, and so the dust pattern is not symmetrical. You'll only get a really nice symmetrical donut-shaped dust coming from a microburst if the horizontal winds are weak. In this case, we have stronger horizontal winds, so you really only see the dust production on one side of the microburst. And here's another example of a dry microburst. You don't see a precipitation shaft, but you see the dust being kicked up from the outflow from this microburst. And here's an example of the rotation that you can see on the leading edge of the air moving out from the microburst. You can see a little rotation here in the dust that's being picked up in this time series sequence. So how do these downbursts form? Well, the first formation mechanism is the evaporative cooling below cloud base. So that precipitation falls, it falls into an area where the relative humidity is less than 100%. That evaporation will cool the air, making it more dense than its surroundings, which cause it to accelerate downward. The second formation mechanism is precipitation drag. So each rain droplet exerts a small amount of drag force on the surrounding air. And although the drag force from any individual droplet is really small, if you put millions of droplets into a small area, they can have a big effect, dragging the air with them down towards the ground. And the environmental conditions for a microburst, well, we need to have a large environmental lapse rate below cloud base. So it's better to have an unstable atmosphere below cloud base that's dry, because we want to have the evaporative cooling, so we want to have dry air below cloud base. Those are the two primary ingredients that lead to a microburst. Secondary ingredients that would enhance a microburst would be a shallow layer of moist air near the surface, Why is that? Well, moist air is less dense than dry air. So if you have moist air down there, it's easier to be pushed out of the way, and it won't affect the density. It'll keep a negative buoyancy associated with the downdraft. And then if the cloud is mostly at temperatures below freezing, then you have a lot of ice that's falling out of the cloud, and that ice will fall faster if it's hail, which gives more precipitation drag, but it will also cool the atmosphere more as it melts and then evaporates. So it cools the atmosphere more. So here's an example of a microburst sounding. So we have an environmental lapse rate that in the red line here, which is 10 degrees Celsius per kilometer. So that's essentially a neutral atmosphere below cloud base. We have a cloud which is raining. It has rain falling from it, but it's evaporating completely, and that's why it's labeled as virga. And so if we take our air parcel from cloud base, which is the yellow line, initially it's going to descend, and as it's descending, its temperature is going to follow the saturated adiabatic lapse rate until all of the water vapor, all of the water droplets evaporate completely. And so at that point, once the water the droplets have evaporated completely, then it's going to follow the dry adiabatic lapse rate down to the surface. So this air parcel starts off at the same temperature as the environment, but then it cools following the saturated adiabatic lapse rate. And at that point, it's about 10 degrees colder than the environment at that level, which means that it's going to have a significant downward buoyancy acceleration. And as it falls as it sinks with the dry adiabatic lapse rate, it's going to remain significantly negatively buoyant on the way down, which means it's going to continue to accelerate downward until it impacts the ground. So let's watch what happens here. So the air parcel makes it all the way to the ground in this scenario because it was negatively buoyant all the way down. So the air parcel is much colder than the environment when it reaches the ground, and it's going to spread out into your gust front and your result of your downburst. So let's take a different environmental lapse rate, in this case 5 degrees Celsius per kilometer. So our air parcel is going to behave the exact same way. So in this case, its temperature is going to decrease, but it's not decreasing as fast as the environmental lapse rate. So initially, the air parcel is still warmer than the environment, which means it's positively buoyant. And so the way it's going to overcome that is through a combination of evaporative cooling and precipitation drag. And eventually, it becomes cooler than the environment, which means it's negatively buoyant. But in this particular case, as it continues to descend following the dry adiabatic lapse rate, it once again gets warmer than the air parcel. The air parcel gets warmer than the environment, and it's going to become positively buoyant. So this is not a good situation for a downburst, and let's see how that air parcel behaves as it descends from cloud base. So our air parcel never made it down to the ground, which means that it's not going to be conducive for a downburst. What was the difference here? The difference was the environmental lapse rate. The environmental lapse rate was more stable than the previous example where we had a neutral atmosphere. So the air parcel is warmer than the environment when it gets close to the ground and will slow down in reverse direction until it reaches the new equilibrium level. So let's look at a sounding to see an example of where we have dry air below cloud base. We refer to these soundings as the inverted V. So this is a Stuvey diagram. The right line is the temperature, the left line is the dew point temperature. And recall that a big difference between the temperature and the dew point indicates a dry atmosphere. So in this case, this dry layer will enhance the evaporation from precipitation that falls into that layer. It's more likely to lead to a dry microburst in this case. And these dry microbursts are very common in the western US, where we have these high base thunderstorms and a lot of common virga underneath them. So that shallow moist layer near the surface, recall that that moist air is less dense than dry air, and therefore that will enhance the negative buoyancy of the downdraft right before it strikes the surface. And if that cloud is mostly at temperatures below freezing, it takes more energy to convert the ice to vapor than to convert liquid to vapor, and it enhances the cooling in that downdraft. Remember, those are the two secondary effects that lead to microburst formation. So wet microbursts. So here we have a different type of sounding where we have very high moisture content in the lower part of the atmosphere. So we don't have a lot of evaporative cooling, but the precipitation drag will be the dominant mechanism for creating the downburst. This situation is likely to lead to a wet microburst, and these wet microbursts are much more common in the eastern United States than they are in the west because of the availability of the moisture at low levels from the Gulf of Mexico. So why are microbursts dangerous? Well, they generate strong straight-line winds, oftentimes greater than 100 miles an hour. They can knock over trees, they can damage power lines, and they can cause aircraft to crash if they encounter one when they're close to the ground. And perhaps one of the best examples of this is Delta Flight 191 in Dallas-Fort Worth in 1985. It was on final approach to Dallas-Fort Worth Airport, and it encountered a microburst, and it didn't have enough altitude to be able to recover from this, and it actually crashed into the ground short of the runway. So let's see how that could happen. So here we have our damaging straight line winds that have knocked over trees. And in order to understand how the Delta Flight 191 crashed, let's do a real quick primer on how an airplane wing works. So we have an airplane wing here in the middle, which is essentially an airfoil shape. It has a leading edge and a trailing edge that are different shapes. And the path length for the air moving across the bottom of the airfoil is shorter than the path length of the air moving across the top of the wing. And what that does is it generates a low pressure on top of the wing, and because the air is moving faster over the top part of the wing, and you essentially have a high pressure below the wing and a low pressure above, which gives you lift. So let's look at these air parcels as they flow across the wing. There we go. And as long as the air is moving fast enough over the wing, you'll generate lift. So here we have the scenario encountered by the Delta Airlines Flight 191. So it's coming in for a approach to the runway, which is off on the right. We have the blue line here, which is the intended glide slope, and the airplane is descending, and it happens to hit the leading edge of the gust front. So what happens when that happens is that the airspeed over the wings actually increases because of the outflow from the storm. So increased airspeed over the wings creates more lift. So the airplane will deviate upwards from the intended glide slope unless the pilot's correct. And that's what happens at position 2. The pilots realize that the wind speed is higher than it should be, or higher than it was, which gave them extra lift. So their response is to reduce the throttle and to pull back on the stick a little bit, or push down on the stick, depending on how they want to deal with it, to get back to the glide slope. And so as they do that, they move into a different part of the microburst. In this case, they get into the area with the strongest downdraft. And then at the point where they realize that they're in this downdraft, they're now descending more rapidly than they want to be. And their response, of course, is to try and increase power and to pull up on the nose. But just as they're doing that, they move from an area of strong downdraft to a region of strong tailwinds, where the wind speed over the wings is significantly reduced. And therefore the lift is reduced, and so now they don't have enough altitude or enough airspeed in order to recover, and they end up flying directly into the ground short of the runway. This scenario was a particularly bad microburst. It was a dry microburst that they couldn't see the rain shaft that they were essentially kind of going to fly under. And even when they told pilots in a simulator that you're going to encounter this particular downburst scenario, 85% of the pilots who were put into the simulator still crashed the airplane, even though they knew what was coming. And the pilots for Delta Flight 191 had no idea, because at the time, the United States did not have a warning system available for identifying these microbursts near airports. We now have the terminal weather Doppler system, which can identify the presence of these microbursts at many of the major airports, which has dramatically increased the safety for these aircraft encountering microbursts. So we can now actually calculate the amount of energy associated with a downdraft by doing something analogous to the convective available potential energy, but this time we're going to do the downdraft convective available potential energy, which will integrate essentially the negative buoyancy below the level of free sink, the LFS, which is a new term, which is the level at which the air parcel becomes negatively buoyant for the first time on the way down. Here we have the downdraft CAPE. The D CAPE is gravity times the integral, or the summation between the air parcel buoyancy, the negative buoyancy, times essentially delta Z between the level of free sink and the surface. And similar to our estimation for the maximum updraft velocities using CAPE, we'll use the same equations for the estimating the maximum downdraft velocities. The maximum, theoretical maximum downdraft velocity is equal to 2 times d CAPE with the square root of that quantity. And the maximum likely downdraft velocity associated with that is the maximum downward velocity divided by 2 because of entrainment and dilution on the way down. And then gust fronts are the name that we give to the leading edge of the cold air outflow from these downbursts. They are typically 100 to 1,000 meters thick. They range from several minutes to a few hours, and they can advance at speeds ranging from 5 to 15 meters per second. And they produce really dramatic changes in the weather. They have a very dramatic decrease in the temperature and very strong straight line winds. When I was growing up in Kansas, it was these gust fronts that really got me excited about thunderstorms, because you could literally see this cold air coming at you from the downburst, and then the temperature would drop 10 or 15 degrees in a very short period of time with these strong winds that came behind it. And it was just really impressive to see the outflow from these downbursts.